cornerstone for this research field. Whatever words I could say now would fall short of describing all of his achievements and the scope of his career. Therefore, I can only say that we are very happy that you share your insights with us in this marvelous field. So without further ado, I would like to introduce you and leave the stage to Professor Di Vincenzo.
Okay, yeah, thank you. Yeah, so I'm very happy to reach out across the ocean and see you on this Easter weekend. But I guess this is the beginning of a fairly intense week for you, and I'll try to touch on a few things that you'll be seeing, but maybe just give you a kind of a general introduction, a bit of the historical line of how we got to where we are now, but also give you kind of a few concepts of what is going on, mainly in quantum computers and mainly in solid state quantum computers. So I'm going to share a screen. I'm going to see if I can keep things set up so that I watch the chat. But also, if there are questions, I'm happy if someone just shouts so that you know, so that I can hear, and I'll stop and I'll be happy to answer questions. Anyway, so today's the masterclass. And as you see, I've entitled it Solid State Qubits, but I'll take a rather broad view of what that means on the one hand, but I will also spend a fair amount of time talking about superconducting qubits because they're showing great success currently. And you know, it's worth understanding some of the basics of that, which of course you will also be reviewing in the course of the week that you have coming up. Now I'm going to be repositioning my screen a little bit so that as I said, so that I can make sure I can actually see the chat. But you can see my slide, and I hope you can see when I move it like that. So now you see a picture of Richard Feynman and a few words from him.
Excuse me, sorry. I think there's a problem with the slides, and at least on my screen they seem shifted. It's not completely clear.
Oh, really? Okay.
That's fine.
I don't. That's strange because my screen share shows it at the normal position. It shows some black at the top and the bottom, but I see everything.
No, it looks good.
Okay. Good. Anyway, so yeah, thanks. We should indeed check these things now and not after I am going for 10 minutes. Okay, now, as I said, I promised that I would be having the chat in front of me, and I'm still not quite there yet. Let me spend a few moments, and you can be reading this quote from 1959, which I think of as one of the starts of the subject that we're talking about today, but only one of them. Here's the chat window. Yes, okay, very good. So blank at the moment, but I'll be having it on my screen right there. Okay, now Richard Feynman, he's a well-known name in physics. He invented a lot of important things in theoretical physics, and he also had a lot of diverse interests and also in how physics would affect the future evolution of computing. So that's why many things that he said are, have been very inspiring to us over the years. So this is a few sentences from a long lecture that he gave in 1959. This is often quoted. The title of the lecture is There's Plenty of Room at the Bottom. And what he means is at the bottom of the length scales of machines. He wasn't only focused on computers, but he had some things to say about that. Actually, in this lecture, he was also talking about motors. And he challenged people to make, could you make a motor that's this big? And someone the year after did. They made a motor smaller than they had ever made, inspired by his thinking. But his ambition was to go way smaller. And of course, this is long before integrated circuits even, so it's long before computers were very miniaturized. But he envisioned that technology would go there, and he says the word circuit. So he was thinking about some kind of electric devices, and certainly he had computers somewhere in his mind in this. And he reflects on the fact that once you get to small scales, the laws of physics are different, or you should use more fundamentally correct laws and than the classical physics that was appropriate for describing many machines up to that time, and that you should indeed use the laws of quantum mechanics. And now he has a comment in here where he says, where is it? He says that, oh yes, he says circuits of 7 atoms. And I think this, I wanted to highlight because this is where he maybe got many of us on the wrong track. So if we had followed him literally, I think we wouldn't have gotten where we are today, because he suggests that that machines of atom size, or just a few atoms, would be needed to see these new kinds of laws. And if that were so, I think things like quantum computing would still be quite far in the future. So the fact that they are really present today means that he wasn't quite right about this, that it hasn't turned out to be necessary to go to 7 atoms or a very small number of atoms to have new kinds of functioning that are really determined by the laws of quantum physics. So, but anyway, this is a very important lecture, and it really inspired much of what today is called nanotechnology, not only quantum things, but just how you make things at their ultimate miniaturized scale and still be functional. Okay, so now this was already a long time ago, but I just wanted to touch on maybe 1 or 2 high points of people that then did try to bridge these kind of ideas to working principles using quantum mechanics. And I won't really return to these old thinkers so much, but just to point out that the subject is already rather old intellectually. And if you ask, how did we first think about quantum communication, which you'll have some lectures on later in the week, one can really credit Alexander Holevo for work in the 1970s. If you want to ask, when did computer scientists first become aware of the rules of quantum mechanics and how it would affect the running of logic in computation, then you should probably point to Yuri Manin and his book in 1980, where he actually predicted quantum computers and rather accurately stated what would really be different about them. I might mention that these first 2 that I've mentioned are Russians. This is a sensitive point these days, that we're not so friendly to Russians, but we should definitely give honor to their great intellectual contributions over time. And these were 2 of them for certain. Actually, the background graphic here is a frame from Manin's book. And if you know Russian, you could read a few sentences there where you would read his very insightful ideas about what quantum computers could be. More directly inspiring for me was the work of Rolf Landauer, who was actually a famous solid-state physicist. So that's rather closer to my subject today. And he explored many aspects of how you would relate physical implementations of devices to information processing, and found very important limits on, or understood what were the limitations of miniaturization, which we're still working through today. And he was a colleague of mine in my past years when I worked also at the IBM company. Let me, I realized I wanted to even put one more thing on my own personal screen. So let me spend a moment, finding one more thing that I want to be also looking at the same time. Okay, very good. I'm back again. Okay, so now I actually want to jump right to the present and then fill in some of the story of today. Now, these dreamers were only imagining that new kinds of capabilities were possible. And nowadays they are actually possible. And you will hear this week, I think, that we've entered in quantum computing, we've entered what's called the NISQ error, the NISQ error. So these quantum computers are not really large scale yet, but they're so-called intermediate scale. And unfortunately, they're noisy. So they're not they're not as precise a machine as we would like them to be, but nevertheless, they already represent a remarkable new kind of technology that really did not exist 5 years ago, let's say, and is under continual remarkable development. But a snapshot of today would say that we now have machines that, and these are just sort of the shiny pictures. I'll come back to that first picture in a moment, but first is a chip of the Google company. You can't see very much. I'll show a little bit of the insides of such a chip in a little while. And it has, this particular chip had I know the exact count, 53 qubits, so quantum mechanical bits, bits of information that, or physical registers that contained 50 or so of these new kinds of bits that are made possible by quantum mechanics. And they also did a significant computation with those. They are not the only ones. This is their paper from now 2 years ago. I think quite significant was that their work could be fully reproduced in detail by a group in China. So this is not just a one-at-a-time miracle event. So a group, a very large and hardworking group in China was able to make basically the same device, but with improvements. So with less noise, with a couple of more qubits. And that's definitely not going to be the end of the story. This is back to the IBM company. This is a sort of outer picture of their device, but as I said, I'll take apart this device. This is a pretty big thing. If you saw a person standing next to it, it's several meters across, so it's somehow hearkening back to computers of the past in its size and complexity. This is in fact representative of the actual record holder currently. This is a device that has 127 qubits. And what's interesting about it is you can actually access, or there are people with the right kind of access permissions who can access this online. It's available on a cloud interface. This diagram down here is an attempt to say something about the physical layout of the qubits. These are actually on a silicon chip, and I'll show you, a more detailed picture of this later, but they are laid out in a regular pattern, and there's each circle here represents a qubit, and then there are interactions possible between nearby qubits. And that has made possible the execution of small quantum algorithms. And I think you'll have something in your bootcamp about this. This is representative of things that you can do with the software called QIST. And IBM also, again, has been very active in making these resources available and teaching people how to use it. And in going from, well, this is some icon of the state of a qubit, but how an array of such qubits, here's a cartoon with 4 such qubits and how you can act sequentially on them and implement instructions algorithmically. So let me indeed take apart this case. So this is a big metal case, and if you look on the inside of it, it looks like this. And this is where those of you who are coming at this from a sort of engineering direction, I think it's worth looking at this. This is a device of pretty high complexity. Whoops, sorry, let me, I'm afraid I have a timer running, so I hope that doesn't run off on me too much. This thing is a system. Sorry, it's going to keep doing that, but I'll have to keep jumping back. Most of this is not quantum mechanical. Most of this is precision electronics engineering, or analog electronic engineering. The actual quantum chip is down here. If you see my red pen, it's in an enclosure, and the chip is just a couple of centimeters square. Maybe I'll stay on this picture for a moment because now finally this gives the picture of, an actual human scale. Here's a technician, or more than a technician, a physicist, an experimental physicist, working on the insides of this device. Back to this picture. Here's the meter scale. So it is indeed not at all a small device. It turns out about this much of it is very, very cold, held at temperatures less than 1 Kelvin. But still, there's actually a lot of electronic equipment in here, and many channels connecting it to the outside world. And most of this is sort of connections to the rest of the world. All connectors go out through the top of this instrument. So it's a big refrigerator, and with a lot of cabling. So these are all individual microwave cables that come in, something close to 100 of them in this device, in order to control, I think I say it in the previous slide, indeed, a 50 qubit device. I like to compare it, though, not really so much to a computer. A lot of people compare these to computers of the past. I think in many ways it's more comparable to particle physics instruments of the past. So this is a synchrotron from 60 years ago. And it's, of somewhat comparable size. Synchrotrons, this is actually quite a bit bigger. Here's a person in this picture. Of course, synchrotrons and particle accelerators got a lot bigger over time. There's no reason why these, fortunately, have to get very much bigger, because improving them does not involve having more energy, and quite the contrary. Much of the effort is involved in keeping energy away from this instrument, and delivering only very carefully controlled energy in the form of microwave radiation into the chip, or onto the chip that controls the qubits. And they are otherwise held very still. They're held at very low temperature, and there's no reason for them to get bigger. But there is a desire or a need for them for us to have more of them. That is, this is a 50 qubit instrument, and we foresee that these should become, say, like million qubit instruments. There's no reason why they become devices of the scale of a supercomputer. They don't need to have so many bits. I don't know what number I would quote, 10 to the 15 bits or something. It's not necessary for a quantum computer to ever be of that scale, but 10 to the 6 bits, 10 to the 7 bits in this quantum form, yes, that they are in fact quite interesting and important for the kinds of algorithms that we ultimately would like to run. So, and I will get to eventually near the end of my hour here to giving you pictures of, actual, more details of what is going on in the inside of these. But I want to again step back and say that, I left a gap of about 50 years between the initial dreamers and where we got to where we are today. So I want to look at this, the road that we took, and it was quite a long one and quite a one with many turns. And the initial start was not obvious. And as I said, Feynman put us a little bit off on the wrong track. So I will begin this story. This is now a major research result of 1970. Not really about quantum computers, but a result which is often considered the foundation of what we know of as quantum cryptography today. I won't talk that much about its functionality, but you may indeed hear about it this week. This was invented mainly by Stephen Wiesner when he was a student, in fact, and in collaboration with Charles Bennett, who was is still to this day an important scientist also at IBM. So he had an idea of what's called quantum money, Wiesner did, and it is indeed a way of, or it's a concept of replacing the security of actual money. So here's $100 or whatever, but it's the dream money. But But you imagine, yes, a normal piece of paper with that is money, and it is normally part of its security is that it has a so-called serial number. It has a unique identifier. So Wiesner proposed replacing that identifier by the states of individual quanta, of individual quantum mechanical states. And maybe the connection with quantum computing is only that he thought that had to be actually embedded in a two-dimensional structure. In his case, a piece of paper representing money, but dreaming forward to it being actually a surface of a chip. But he thought of them, the need for them to be in some kind of array and for them to be held in particular states. He had two ideas for what these could be, both highly, imaginary in the year 1970. One which would be that this would be the state of a single photon of light, and that's what the cartoon is meant to indicate, that these are states of polarization of one quantum unit of light. That's really extremely impractical to imagine that you could somehow store a photon of light in a structure, but you can actually make cavities and store light today, not in such a small thin space, but you can make little cubical structures in which photons will live, not for especially long, but actually that capability has grown over the years, but was highly imaginary at that time. But the one that actually connects more closely to my story is that Wiesner gave another example, and he said, well, these could also be the spins of atoms embedded in solid. So, and in fact, that was highly visionary for another approach that's used for information processing, that quantum information processing, that you use the states of individual atoms. Now, I would say, and he was indeed prejudiced by the thinking that was represented by Feynman's work 10 years earlier, that if you want something to be quantum, you better make it just individual atoms, one atom at a time. Now, that's also highly impractical. We know how to trap individual atoms nowadays. And that is to this day now one route for quantum computing, that you would trap and manipulate individual atoms. But I want to tell you a little bit how that developed. That turned out to be not indeed the only route. But what gave this a really big boost was the realization, and now I jump many years further in the future from this, that actually it started a little earlier than this, starting around 1980, Manin first announced thoughts, but there were really thinkers, mainly from a more mathematical direction and computer science direction, who learned the rules of quantum mechanics and found that if you formalized it in the right way, you could think of it as a kind of new programming language, what we now call QIST. Of course, that was not invented till long later, but just in a sort of purely mathematical sense, it was understood as a new formal system. And this picture is Deutsch. So Deutsch was indeed one of the really pioneer thinkers of understanding how you could take these rules from physics and make them rules for computing, and then invented several new kinds of algorithms based on that. But then it was the work of Shor that really culminated this. And he was an applied mathematician, computer scientist, working for the telephone company in the United States. But he saw that using these rules, that you could do quite amazing things, and in fact, things that were extremely potentially disruptive for methods in cryptography, for example. So this year was kind of a watershed year, in fact, that it made it suddenly clear that it would be of high value to realize physical machines that would do quantum computing, and not just bits one at a time as we use them in cryptography, but have a whole array of qubits that would be working together as a whole system. Now, having said that, it was still enormously far in the future. That is, the developments in, let's say, experimental physics were still at a very low level of maturity in order to achieve what was needed to run Shor's algorithm. So here I can tell a bit of a story of what I was thinking about at that time. I was earlier, I was just beginning to work in this field at that time, and these results came along. And I, from the point of view of, well, more from solid state physics and more thinking about experiments, realized that we had a lot of work to do. And this was one of my first surveys of the situation. And I can look back and see how I got things, well, a little bit right and also a lot wrong. That first of all, I tried to tabulate all the potential, carriers of quantum information that were, conceivable based on what existed in the laboratory at that time. It was 1995. And some of them have indeed been quite, good, have really been working out very well as implementations of quantum computing. I can take trapped ions as an example. Individual electron spins in atoms, but these are more the Feynman path, and in fact, I could say I really missed a whole path that was not based on the Feynman principle that you had to find individual, atom scale devices. I even said, well, how about the state's interior to nuclei? That was, I realized at the time it was a highly speculative or unlikely route, but had the interesting feature that the potential switching time was really remarkably fast. This is 10 to the 19 seconds. But I think we're not at all at that scale. We are indeed at the scale of the time, the times to go from step to step in a quantum computation, somewhere down in these ranges, in microseconds, say. This was an initial tabulation of how quantum mechanical these are, which has to do with the so-called coherence time. I'm not going to try to explain that here, but maybe that will be covered more as you go along. But it's basically the length of time over which the Schrödinger equation is a good representation of the evolution of a quantum system. So these times are unfortunately not very long, mostly. There were even in 1995 instances where it was very, interestingly long, actually hours long. And that made it interesting, or makes it interesting to this day, in things like quantum money, where you actually want your money to live a pretty long time. This was one of the cartoons that I offered at that time of a sort of nano instrument but this was more concerning the concepts of how you would use nuclear spins for quantum computation. And that had some success over the years, but not at all with my sort of imaginary instrument. The principle of this would be that here are protons sitting at the end of a tip approaching a surface, and the proton has a spin 1/2, which means it has a two-state quantum mechanical system involving its angular momentum. And you can indeed manipulate that two-state system and call it a 0 and a 1 and do some computation with it. And in this concept, this tip was facing a surface which also had some hydrogen sticking out from it. And so these tip would go along and interact with the hydrogens on the surface. Never happened. So this was a bad prediction, but it was mainly just to get people thinking. Okay, but where, well, I want to tell the story. Let me jump over the next slide just to tell the story that where we really missed it. That is, that this completely missed a major possibility for how you would approach this that had already been maturing in solid state physics for some time. And so this steps back in time 10 years from that, in 1985. This was pre-qubit, so no qubits, but was a highly important experiment as a matter of principle, because it showed that macroscopic objects under the right conditions could also obey the laws of quantum mechanics and could have the dynamics appropriate for, achieving qubits, even though the devices were actually circuits. So here's, a schematic sketch, but I have somewhere, well, in a few minutes, I have a slide that shows the circuit. It has familiar things but you would say familiar in classical physics. It has capacitor. It has this, which is not necessarily so familiar, but which is basically a kind of inductor. So basically another kind of electric circuit element. It's a specific kind of nonlinear inductor. It also has resistors, and those are bad. Those are not good for quantum computing, and we've learned over the years how to get rid of resistors. But this work in 1985 was enough to show, these are the three researchers who were involved, who remained active and strong workers long into the future, long into that, after this work. They showed that if you neglected the resistor, that the dynamics of this circuit was predicted to be that of a particle that was rolling around in a potential well, actually a metastable potential well, but that when it was in this part of the potential, it would be confined. And according to the laws of quantum mechanics, that confinement would lead to quantization of the energy levels in this well. And they proposed that it would indeed act like an atom, like an artificial atom, and that you could do spectroscopy on it. You could cause transitions from the ground state to the excited state of this kind of atom. And that was very inaccurately, but convincingly shown that at least there was some indication of that behavior in the measurements done on this circuit. So they did indeed announce that they had achieved energy level quantization in this electric circuit. Now, this has a lot to do with superconductivity. So it has a lot to do with the absence of any dissipation intrinsic to the circuit. But it also has to do with really the solid state physics of superconductivity, that it involves a particular kind of collective electronic state, that even though the underlying states that achieve this are the states of, let's say, millions of electrons in pairs, as it turns out, but they all act as one, and they all act in a sense as if there's just one particle rolling around in this potential, and thereby achieving individual energy levels. So that was an important proof of principle, that you didn't have to go all the way to the scale of individual atoms in order to see atomic-like effects, including even states which you could label 0 and 1 and call the states of a computation. But this is finally what it evolved into, and I would mainly focus on Martinez. This is the first author of this paper, who as a student did this work, but then over the years pushed this very far, this exact circuit very far, and achieved very close to ideal operation, but not quite close enough, but quite close to the perfection that we had in mind for a quantum computer. Now, I can say I'm going to tell a little bit further of the timeline of specifically of these superconducting devices, because this work from 1985 was indeed the immediate predecessor of the achievements of Google and IBM. Indeed, Martinez led the Google research, and many of the workers at IBM were trained by John Clark, who was the professor who supervised this experiment in 1985. And I will also feature work of Yale University, and that was strongly pushed forward by the other author of this, Devore. But let me also back up now and give a thought of, why was it hard? Why did it take many years, tens of years to get this? And I would say it was because we could realize already, well, in the 1990s, we could realize that there were certain things that had to be achieved in the laboratory in order to go from, just physics experiments to quantum computation. They mostly involved enhancing capabilities that we could see were present in experiments, but had to be tremendously improved and all brought together at the same time. And I'd say, in a sense, this bringing together was the hardest part of the work. And this checklist of 5 criteria was something that was rather instrumental in, seeing what was promising, seeing what improvements, had to be focused on, and where, progress could be made. And these are just said in a few words, but these words convey a lot of meaning, and they actually all tell the story of very hard experiments that had to be achieved. So the first one just says the word qubit. It says that you had to achieve devices which had well-defined and reproducible 0 and 1. You had to make them into arrays. You had to have many of them. You had to really strongly control their state. And each one of these next few steps indicate, discrete capabilities, all of which were extremely hard in 1995. I'll put a time, an approximate time on when these were being discussed. Start them all in the 0 state. That's sort of a very normal thing you do with the computer. You clear the memory. But that is often not necessarily an easy thing to do at all with the quantum system. And that's part of the reason why you have to go to super low temperatures. That the getting rid of the thermal agitation so that it's possible for the system to sit in its ground state is covered by this very innocuous looking criterion. This says the story of coherence time, and this is all about low noise, basically. As electronic instruments, these are extremely high precision, low noise electronic devices, and that's partly the story of having low noise. And in the quantum mechanical language, it's you say it has high coherence, high quantum coherence. This next one says you have to actually be able to make it programmable, that actually have an instruction set and have it run a procedure for this device. Experiments like this had, no instruction set. You had a radio generator, you turned it on or you turned it off. That was about the whole instruction set of this physics experiment. So it had to go from that, one on-off switch to, in fact, hundreds of channels, each carrying instructions to the experiment. And then finally, you have to be able to measure a system. You actually have to be able to observe it and say, aha, it is in the 0 state or it is in the 1 state. And that's a famously difficult thing to do with quantum systems. And but was part of the story of this experiment that at least to some precision, to some rough level, there was actually a way of detecting the state of the system, but very intrusively. That is all these dots, which I don't know if you can even see them, but they're very fine dots that make a kind of fuzzy curve. These all require lengthy and destructive measurements. Destructive in the sense you have to, it doesn't burn out the device, but you have to wait quite a while and to let the system settle down again before you run experiments on it again. So all of those were kind of wrong from the point of view of quantum computing. But nevertheless, this insight that electric circuits were actually capable of embodying qubits was highly inspiring. And but still, it took many years before this work came to fruition. But it was understood, I guess the next thing that was really understood was that this represented a kind of toolkit. And I give credit, this was one of the authors that further and worked out the theory that said that you could indeed make large electric circuits and systematically analyze them, but also use them as a design tool to create functionality of the sort that you want. So starting in his lectures in the 1990s, and that's indeed about when we started to use the word qubit, and where workers in this field started to turn their attention to achieving qubits. The first actual achievement of qubits, let me jump to this, was not so spectacular. It was actually first achieved in a laboratory in Japan by these workers. And they took some existing experiments, modified them in a certain way, and were able to achieve, first of all, 2-level systems. control over them, so they could vary the energy gap between these systems. They could apply pulses to them so as to change the state on demand. And they could see quantum superpositions. So, but this was indeed a leap beyond what was possible before, but the quantum superpositions are seen in interference fringes, and you have to believe that these couple of spikes in this curve are actually interference fringes, so very far from what you would see in even a simple optics experiment. So as some signs, I say just very, very first signs of quantum mechanical operation, but nevertheless it set the stage. And the next step in this timeline was already a really big leap, it turns out, in the sense that this data, in a very carefully designed electric circuit, this is indeed the work of Devoré and coworkers in Paris, that with this designed electric circuit, well, here you see a first time actually, micrograph of, or photograph of the actual electric structure that made this circuit. But the specifics of, exactly what circuit elements were used, circuit elements were used, exactly how to place the capacitors, how to place the measurement devices, had made tremendous progress and resulted in real, genuine interference fringes, still not of the quality that you could see in, say, atomic devices, but a considerable step in that direction. This was, however, not the end, that there were several more iterations of designs that were coming. And I focus on what really took over was work at in both physics and applied physics at Yale. And I say it that way because it was sort of a collaboration between people with high engineering expertise and also high quantum physics expertise working together, that they understood certain basically filtering concepts that made it possible to greatly further reduce the amount of noise and increase the quality of quantum coherence. And this finally was a first achievement of what are now known as the transmon qubits. I don't think I have it on the slide, but that's a particular style of superconducting qubit that is now highly optimized for operation and for the achievement basically of the 5 criteria that I sketched out. I did jump over, but I wanted to say that this is actually not such a familiar name in quantum computing, but is someone who is highly honored in the technical community, in the community of high frequency electronics, Daniel Prober, and that his knowledge, quite apart from the quantum physics knowledge, was highly crucial in making progress. And what happened in the subsequent years, and now I'm looking at this sort of 10 years in this period of time between, say, 2002 and 2012, was a continual steady increase. This is the coherence time. And it's really a big figure of merit for single qubits. And down here is the Japanese experiment, so the coherence time is barely measurable. But you see on this log scale that the Paris experiment, but then mostly Yale experiments, took us up by many orders of magnitude over the course of that decade. So a successive improvement was in fact possible and was achieved. Now, I have things to say. Of course, this is far before the present, but this has somewhat flatlined now that after about 5 orders of magnitude of improvement of a kind of, we were optimistic to say a sort of Moore's law, so it has kind of gotten stuck. But it got stuck at an interesting level, that is where quite high quality quantum operations became possible already about at this time. That's what the red dotted line was indicating, was sort of a point at which it became realistic to look now at many qubit devices and run, I won't say algorithms, but maybe protocols on them. And that's the era we've been in for about 10 years, but still gearing up and getting all the engineering capabilities to achieve the kind of devices that I showed you were coming along about 5 years ago. Let me say a few more words about such devices. this the Google device with the 53 qubits is, well, their code name was Sycamore for it. It had a layout of something like this, but again, rather schematic. What I think is maybe more informative is to, let me not do this one, is to say, I'm sorry, I thought it was the next slide, more slides. Okay, sorry, this is more physics ideas that I will come back to, but I think it's now the next slide, yes, okay. This is a look inside one of these modern day chips. Now this chip's already maybe 4 years old because it's, quote, only 16 qubits. But well, one can surmise that it's highly representative of what you would see on a Google or an IBM chip today. However, they've stopped showing these kind of details. So you have to look back a little bit farther in the literature to see really specific details of the qubits. Now, even here, you have to be given some interpretation. The 16 qubits are these sort of squarish structures. Note, these are not very small. This is not nanoscale. This is a scale you can see with the eye if you look very carefully. I can indicate here 8 of them, and there are another 8 here. So those are the 16 qubits. And then there are various control structures, but there's basically a kind of transmission line that just for space is all wrapped up, but which just basically runs from one qubit to the other one. And there is actually a kind of exchange in a quantum mechanical sense of microwave photons between qubits that are connected by such transmission lines. And that's the basis on which they can run programs. That is, you can actuate the participation of these couplers. You actuate it actually by sending in microwave pulses from the side, so to speak, that is launched, actually created at room temperature, sent into this instrument through cabling, but onto the chip, and then via individual transmission lines into these qubits. So there's, in fact, a wealth of still engineering to be done to make these better, and they're, each generation is really quite different from the last in the engineering aspects. Also, but to a somewhat lesser extent, actually, the actual superconducting aspects of the qubits themselves. Let me spend a few more minutes. I think you can understand that I cannot, in an hour, cover very much, but I thought this is indeed most of what I was going to say. I thought maybe I'll give you a little bit more of a physics understanding, but where do I say it here? Yes. I'll do these in reverse. So this is a slide really now for the kind of real physicists, people who want to think of hardcore physics. So this is the Hamiltonian. This is defining the Schrödinger equation that these qubits obey, and from which we use this to describe the energy levels, describe the fact that they have energy levels 0 and 1, and so forth. I realize this is in a kind of code, but I'll decode it. We've done it for, I'm discussing it here for just a one-dimensional chain. You saw that there are more complex chain structures that are actually in place, double chains, but now there are multiple chains, interlinked chains. But this first two involve kinetic energy and a potential energy. And it's actually rather easy to say what these are if you use a physical analog. And I'm going to back up, but all of these pictures, I have somewhat too many pictures here, but this Hamiltonian, just for one qubit, is actually the same as the Hamiltonian you use to describe a pendulum. So that's another macroscopic object, but indeed the so-called transmon qubit is in a very precise way analogous to a pendulum. So the dynamics of a swinging pendulum. You see here the cosine is the potential energy law of a pendulum in gravity. And this, well, this is, I can ignore this. This is momentum squared. So this is the kinetic energy of the weight on the pendulum. So everything can be understood by strict analogy to that. One thing you can say is this potential is not so different from being harmonic. Of course, if the swinging of the pendulum is not very far, and for that reason, the energy levels are understood as being close to those given by Planck's law. That is, energy levels are separated by h bar times the frequency of this electric circuit. That's not quite so because of the anharmonicity of the system, and that's the anharmonicity is actually very important for its functioning, it turns out, because many of the manipulations involve making transitions with a specific energy of the, in fact, these are microwave frequencies. For example, 6 gigahertz. And you actually, irradiate these with 6 gigahertz radiation in order to cause transition. It's important that these not cause transitions between other pairs of energy levels in this spectrum. So that's one concept about these. The other thing that I can comment, let me not bother with that, but when you couple them, I described that there are certain electrical couplers. It's not so different from having coupling just via a spring, some kind of torsion spring. I give some provisos here, but I use this to mention some of our current work. We're wondering, is this a good idea? And it is quite clearly a good idea, but we find it places limits on how you use these. And an interesting fact is that, to connect it to other physics, and maybe a few of you find this interesting, that this is not actually such a simple classical system either. If you do such an experiment, you have two pendulums and you have some coupling between them, you can find they actually can undergo quite irregular motion. Actually, I had no plan to do this, but they are somewhat analogous to what a little toy like this would do. And well, the battery's a little dead on this, but you would find that this can have, under the right circumstances, quite irregular motion. And you can document that. That's done by techniques introduced by Poincaré's. This is a so-called Poincaré section. And with this, we can document the fact that the classical dynamics is what's called chaotic. And this has some dangerous consequences for using these in quantum mechanical systems. And we believe it does, in fact, limit how the Google and the IBM experiments, or how those computers actually work. And some of the put some limits on how reproducible, in fact, the devices are. And there's certainly no one who can promise that, or we cannot say that there is a straight path to the million qubit device. There are many, many things that need to be improved by further trial and error and seeing what to do and what to avoid. I'm pretty much at the end of my lecture. I wanted to, I have a few pictures at the end that are just meant to provoke or to give you some thinking. That was a little bit more about the chaos, but these are two of my, well, kind of favorite paradoxes of computing and of the large quantum devices. So this name you saw earlier, it was involved in the quantum money discovery, but he's actually famous for saying there's no lower limit on the amount of power needed to run computing. And this is true both quantum and classical, but it's very much a matter of principle. And well, this says 2% of United States electric consumption. I'm afraid it's even a little bit bigger now, is devoted to computing today, despite the fact that in principle, no power is needed to run these. The same can be basically said of quantum computers as well, but they could also in principle be run without power, but in practice they're run with lots of power. And that has to do with, this is another thinker that I haven't mentioned before, but Margolis observed that quantum computers could run on their own and compute. But in fact, it's the only practical way is to really drive them and to measure them intensively. And in that respect, it becomes closer to a particle physics experiment. This is a detector at Fermilab. As I said, I don't think the quantum computers will ever get this big, although I have seen schematics of ion-trapped quantum computers that at large scale, and they would say it would actually fill a large warehouse-sized room. We don't think in solid-state devices that they ever need to be so large. So I think I'll stop there. So that's the beginning of your boot camp. I guess the technical beginnings. I had a few more things about circuits, but I'm not going to say them now. And this outline, well, just says one or two of the things that I just said in the lecture. So I think I'll stop there. And as I say, I wish you luck, and I'll also be happy to take any questions if there are any.
Thank you, Professor De Vincenzo. Maybe we can all unmute ourselves, and at the count of 3, we give it to Professor De Vincenzo an applause. Quizás nos podemos desmutar y darle un aplauso al profesor De Vincenzo a la cuenta de 3. Ok, 1, 2, 3.
Okay, thank you. I see the clapping icons also, which we use a lot in Zoom sessions as well.
So if I may, I can make some question that I have very long time in my head. It's about the universal set. I was wondering if this universal set is required to be only unitary operators.
Not quite, but I would say almost. I imagine you'll have some detailed lectures about this. And of course, quantum evolutions do not have to be unitary. But the only way they can be non-unitary is if the system is interacting with an environment, and that usually means something noisy. And so usually non-unitary comes along with being something where you lose coherence, you lose really the special aspects of quantum behavior. Now, having said that, we actually know that there is a whole theory of error correction of quantum computers, and it says that some degree of non-unitary evolution is tolerable. That is, however, it represents errors that have to be fixed, but it is possible to fix them. And a lot of work is done in diagnosing exactly what goes on in the IBM or the Google device when they run a gate. And it's supposed to be unitary, but they can say, well, it's 98% a unitary gate, but then there's a 2% something else, and they work very hard to figure out what that something else is. And sometimes it is non-unitary. It's also, I'd say as often, it's actually something that's unitary, but the wrong unitary. And those are kind of equally troublesome for current day quantum computers.
Okay, thank you.
There is a question on the chat. Diego Duran asks, quantum computers could become desktop computers?
Yes, I see that. Thank you. Not easily, but well, we would say that there are already desktop instruments that do quantum information processing, but that's not quantum computing. But you can already buy a box that will do quantum cryptography on the glass fiber network. So some quantum things can be done with instruments on the desktop. The problem with desktop quantum computers is, again, the noise story and the fact that the main way we know how to limit the noise on any quantum computers we know how to build currently is to go to very low temperatures. So now it is possible to make a device that's only maybe this big that will go to helium temperature. And if you're willing to imagine you have some helium refrigerator sitting on your desktop, then it's maybe conceivable, but not soon. Now I see another chat. I can read it myself. So Luis Vioria says quantum computing can be used with cryptography to try to develop the quantum money. Yes, possibly. What's an active area of research are so-called hybrid devices, where you have both devices that will process quantum bits, but also ways of basically releasing that quantum bit and sending it onto a network. So we call that, flying qubits. So we go from standing qubits to flying qubits. And if you have that, then you can actually mix together quantum computing and cryptography, and also including the possibility of some kind of implementation of quantum money. So I see a hand up of Ms. Rojas. Okay, there's also something in the chat. I'll read the latest thing in the chat. Professor, what is the main goal in quantum computing field right now? Delete noise, more qubits? There are many related efforts. I think you can see my own prejudice is that we still have to work really hard in the noise reduction side. That's to achieve devices of really higher capability. But we have already devices of interesting capability with 50 or 100 qubits. And there's a lot of effort devoted to seeing what could we get out of them. We can't run very big algorithms on them, but what kinds of algorithms can we run on them that are interesting, that can be useful? And I'm not a specialist in that, but I believe you'll hear more about that in the week. And I think, more creativity will be valuable in getting the most out of the small quantum computers that are existing now. I say small only conceptually, because they're actually big, very complex machines. Okay, so anyone want to unmute and actually ask a question? As I said, I see a couple of hands up.
Hello, it's me.
Yes, Milagro.
Hi.
I hear you.
Okay, it's about the qubits itself, because when you talk to me about quantum, I think about particles, but a qubit, I don't know if it's exactly a particle or what is a qubit? Exactly, what is a qubit?
Yeah, well, good. That one could have philosophers and scientists and mathematicians all commenting on that question. That's a very deep question, because a qubit is okay. Well, I'll try a few sentences of what these different thinkers would say. You need to have, first of all, qubit is sort of a conceptual thing. It's a carrier of information that is based on the idea of a bit. A bit is something that represents two possible states, a 0 or a 1. But when we say qubit, we mean it has some enhanced capability, which is that yes, it can be a 0, yes, it can be a 1, but it should be thought of actually as a wave function. And now I have to use the quantum mechanical language. And because we know systems where you have a state, a 0, which is a wave function, like a harmonic oscillator wave function. And we have a state 1, which is a different quantum mechanical wave function, but we can also make superpositions of those states. So we have something which you would say is a superposition of 0 and 1. And if I still had my slides, but I'm not going to bother showing this, this is exactly what we think of in this business of the pendulum. Mm-hmm. That, classically you say the the pivot of the pendulum, or the end of the pendulum, is a particle and it's moving and it has a definite position. But in
Okay.
quantum mechanics, it doesn't. It has an indefinite position. It has a wave property. It's smeared out over a certain distance. But there are different states that are smeared out in different ways, and that which we call the state 0 and the state 1, and then even states which are in superpositions in the sense of waves. And that gets you most of the ideas of a qubit, that it's a new kind of information carrier because it has this added property of superposition, this wave-like property.
Okay, nice.
Okay.
It's super interesting. Thank
All right.
you.
Yep, you're welcome. I see Timothy, I see Mauricio.
Hello. I have two questions. First, I was working years ago in IBM Quantum Experience. It's like 8 years ago. I don't know. I read something in the Nielsen book about being able to put any operation as a unitary operation. I mean, I was working about the interaction of a entangled quantum bit in a, I don't know, in a potential, and how to work it as a function of the gates that was written in the IBM Quantum Experience. I read that it was possible. It is possible. It's to write anything as a unique way to write it as a universal quantum gate and put it in function of the quantum gates written in the quantum experience. I don't know if it's possible.
The quantum experience programming language, now called QIST, it wasn't 8 years ago, but now it's called QIST. Yes, has a full expressive power that you could run. You could very easily write like the Shor algorithm, which involves a sequence of gate operations, of logic gate operations, which are unitary. We've used this word several times because it has to manipulate this wave state, has to manipulate this wave function state. So one can express that easily in Qiskit. One cannot run it because the hardware is not accurate enough to run a long procedure like the Shor prime factoring algorithm. So I don't know if that answers or that addresses some of your question anyway. So yes, the framework is there. We know, I'm sure the framework can be improved, can be optimized, but the framework exists for implementing algorithms, which are in the form of unitary operations.
Okay, thank you for that answer. I have another question. My brother is here. Is also in physics. He have a question for you.
Yeah. Okay.
Hello, teacher. The question is, what of the three pictures, dynamical pictures of quantum mechanics, is best suited to describe quantum computer? Schrödinger, Heisenberg, or Dirac? What is working to study?
Well, we use all three, and all of them are, of use. I'll vote mostly for Schrödinger, but I wouldn't want to do without Dirac, and I don't need Heisenberg that much. But that's just one practitioner's view. But quantum computing uses a lot, not every single feature of quantum mechanics, but many, many of them. So it pays to be very well trained in quantum mechanics to really get deeply into quantum computing.
Thank you.
Now, I've been a little bit neglecting the chat. I don't know if I should try to pick it up. I still see hands, though. It's always easier or more interesting to interact with voices. Mauricio, do you want to ask your question?
Yeah. Thanks, Professor, for this opportunity. We are glad to have you in this bootcamp. Um, I don't want to take much of the time because I don't know how much time do you have. We have still some questions in the chat, but I wanted to ask, this is a bootcamp for Venezuela, for a developing country. And I would like to know, what do you think is the future of quantum computing in terms of providing some influence in the world? How do you think it's in the near future that we will have quantum computers that will be changing our lives in an important sense?
I think not in the near future, but I think, well, I mean, I could say we have them today, but I don't consider them very highly capable. But I anticipate their capability will grow. I think when they exist, they'll exist on the cloud. So actually, you know, in the right collaborations or in the right research projects anyway, it will be possible for people anywhere in the world to make contributions to such research or to the research of trying to use quantum computers. As you see, my emphasis is on the improvement of the hardware. That's, I think, not as straightforward for people in the developing world to contribute to, but not impossible for sure, because, you know, I think that I have used really good lecture notes on microwave technique from a professor in Thailand, to give you an example. And, you know, there's really good expertise in things, and you say, well, okay, of course, the first world knows all that, but that's not always true. That is, that things get out of fashion. And, you know, it turned out that, you know, microwave analog electronics turned out to be quite important for quantum computing. And that's not a, you know, sexy area. You do only digital, you know, if you're really into microwave technique in big companies or something like that. And so knowledge of, you know, older techniques of things that are not, you know, so hot suddenly become hot again. And sometimes the expertise has only been fostered in you know, other parts of the world and then comes back again. So I don't know, that's only one, you know, small anecdote, but I had a few slides I didn't show, but which had to do with, you know, actual electric components that are used. And on the one hand, they're very old type components. You know, I can point to one, the so-called microwave circulator that was more or less perfected in the 1960s. But now there's a need to sort of re-perfect it, you know, to revisit it. And I don't find it's research that's being picked up very much in the bigger world. And so, and it could be possible in even a very small lab to focus on components of this big complex system and make a real difference.
Thank you. Thank you. It's very interesting. I don't know how much time do we have, Antonio?
Well, I think what I would appreciate, I maybe would be happy to go in 5 minutes or so, but I think I'd appreciate a moderator. In other words, I've lost track of where I was on the chat thread, and if one of you would pick up any that you think are particularly of broader interest, I could still address one or two of them.
Certainly. There's a question from Luis Viloria. Qubits are enhanced bits, so can we improve the potency of simulations if we could use qubits instead of normal bits?
Yeah, good question. Because simulation, of course, is a big area of computing, and there are types of simulations that would apparently have nothing to do with quantum mechanics, and yet there are good algorithms using quantum resources for solving them. These are like optimization problems, and that's the basis of one whole branch of quantum computing applications. And then there's the situation where you simulate things that are themselves quantum mechanical, and you know, chemistry or simulations of molecular dynamics are one example, and that's a more obvious one where, you know, quantum mechanical things can be more capable. Now, having said that, that's remarkably complex question of how you really use a quantum computer to gain a new advantage in, solving for the dynamics of proteins or something like that. But people are working on it, and there is indeed some chance that this extra potency of qubits could make a difference, and there are some small demonstrations that it can.
And I have a last question it comes from YouTube, and it's how will the interface between data science and quantum computing evolve?
Yeah, thanks for the question from YouTube. I'd say I don't know. In our laboratory, and I work at the National Lab in Germany in Jülich, we have big data scientists in our supercomputing center, and they believe, I think they're looking farther forward than I am, that the supercomputing center will evolve into a more of a hybrid system where you have, supercomputers as we know them today, based on hundreds of thousands of CMOS chips, but then working together with things like quantum computers, but also others like neuromorphic computers and other kinds of analog computing devices, and then working together to solve big data problems. I have no special insight into that, I would say, but people in our supercomputing center are interested and believe that there is some evolution into that for their future.
Just to finalize, would you be open perhaps if the student to contact you via email later for questions or?
Sure. Yeah, I'd be happy to do that. If I'll look out for any further questions today or during the course of the week, if I can be of help.
We are very grateful for that.
Okay. So indeed, I think I will call it a day, but I think you have more. Of course, you have much more during the week, and I wish you luck in all the hard learning that you will do in the course of your week.
Thank you very much.
Okay.
Thank you.
Thank you. Bye-bye.
Bye.
So we stop the transmission from YouTube. So see you tomorrow. No, see you on Monday, guys.